developing a whole bunch of formalism, which we'll continue to do today, and then hopefully talk about some physics at some point. So what we're talking about is this idea of operator order representations in phase space. So if we want to look at representations of operators that are functions of the canonical variables, or equivalently functions of A and A dagger, then we have to worry about the order in which the operators appear if we're going to substitute the operator x and p with the variables x and p, or equivalently A and A dagger. And so the way we do that is we say, okay, there is in principle some power series representation of my operator, which is a function of A and A dagger, written with some power of A dagger and A written in a particular order. So we have our normal ordering, our anti-normal ordering, and our symmetric ordering. Okay? And so we then define the representation of this operator with respect to that ordering as taking this power series and substituting where we saw A, the complex amplitude alpha, and where we saw A dagger, the complex amplitude alpha star. Okay? Now, we'll come back to the question of whether or not this function converges. There's no guarantee that this is a meaningful function. We'll come back to that question in just a little bit. So that's what we seek. That's the way in which we're defining our representations on phase space. All right? So in order to do that, we invoked a whole bunch of formalism. One of the things we appeal to is the idea in classical probability theory of the characteristic function, which is the generating function for moments, calculating moments of a probability distribution. In some sense, that's what this is. I mean, these powers of products, they're like moments of the distribution. So if I looked at, say, the expectation value of either the I, or plus or minus I, Y, X, where X is a random variable, that's just the Fourier transform of the probability distribution. And as we showed, we could derive moments of the distribution by taking derivatives of the characteristic function, because that brings down powers of X, right? So that's sort of a guide of how we're going to get at these power series by looking at these kind of Fourier transforms. So when we now go to the quantum world here, what we do is we say, okay, instead of thinking about these just plane wavy-like things as functions, let's look at the kind of operator equivalent of that, which are the displacements in position and momentum, phase-space displacements. And those operators have some very nice properties. And one property is to think about them that they represent a complete orthonormal set of operators. And so they are kind of the natural operators in which to decompose other operators on phase space. Okay? And so the notion of orthonormal here is with respect to a specific construction of what we mean by the inner product between two two operators. So we invoke the, now I know it's that Hilbert-Schmidt inner product between these two operators. And so what's true, and I don't know if we've proven it, but we will in homework if we haven't done it in the previous homework, is that the trace inner product between these, defined this way, is they're orthogonal, okay, with this particular normalization, okay? And so moreover, a much harder thing to show is that they're complete. Not only are they orthogonal, they're complete. And as I said, it's sort of by tradition, we look at the D daggers as opposed to the D's as the orthonormal set. But this set is a set of, complete set of projectors onto operator space, okay? So if I integrate over all these guys, I get the identity. And what that enables us to now do is project an operator onto phase space by saying, okay, let's look, for example, at what is the expectation value of some operator A? Well, that's, by definition, the trace of the observable with the state, the density matrix. And since the density matrix is Hermitian, I could put a dagger there, wouldn't do anything. That's the inner product between A and the density matrix, right? According to this definition of the inner product between operators. So I just tack on rho onto this, and I get this. Okay? So this gives us, this is really, in some sense, the whole story that allows us to look at different representations of operators on phase space. And you should think about it like Fourier analysis. Right? In Fourier analysis, if I have a function of x, that function can be written as a weighting of plane waves weighted by coefficients. And what are those coefficients? Well, those coefficients are the projection of the function onto the plane wave, right? This is, you know, k f, if I want to think about it in Brockett notation. And that's what's going on here. I take this is not what I wanted to say. So it's exactly, there's some, sorry, this is A. I'm saying something that I could. I've confused two things. Pardon me. I have two different ideas, and this is not correct. So let me back up. What I said was sort of true, but not completely true. Let's skip a step. Let's go back to this. So now let's look at A. I can think about A in this kind of picture as that, right? And now I'm going to plug in this. So that says that this superket is okay? So that's a kind of shorthand for the following statement, which is really what I meant to write. And I confused two things, so I apologize for that. This is the inner product. This is the trace of A with D. And D. So now, this is like saying I take the function, I project it onto the plane wave, and that's kind of the Fourier coefficient. And then the total thing is weight each plane wavy thing by its Fourier amplitude. Is that clear? Okay, sorry. We'll bring in Rho in a moment. Rho comes in just a moment. Okay, so now we have this decomposition allows us to instantly write down this. Why? Because of this beautiful relationship written here, which is that we know how to express the displacement operator in terms of an ordered power series. So what we know is that I can define these operators d sub sigma as e to the sigma times the magnitude of alpha squared over 2 times d. And these guys are instantly recognizable what their ordered power series are. Why? Because, well, if I look at the case d equals plus 1, using the Baker-Campbell-Hausdorff, this is normally ordered. So I could just write out the power series, and I get that. So here it is. There's the power series. These are my CNMs, right? And similarly, if I put d equals minus 1, then I have the anti-normally ordered product. And I see that's automatically. So they have the same coefficients here, or with those orderings. Okay? So, using that, now we play the following trick. So, e to the alpha squared times sigma times e to the minus alpha squared times what I'm writing, 1, right? So I can plug that in and write more generally the following. A is equal to the integral over the phase space normalized by pi, the trace of the operator with d minus sigma times d dagger with plus sigma. You buy that? Because I can shove this in. This is a number, so I can put this guy, that's d minus sigma, right? So I have kind of this duality between normal order and anti-normal order. Okay, so far just math. There's going to be a lot more of that. So now, we can just plug this in, right? This is equal to nm minus, plug in those representations right over there, right? And that says that this is going to be equal to Cnm sigma, the sigma ordering of a dagger to the n, a to the m. Just plugging in d sigma, whatever it is. And what are the CNMs? Well, the CNMs they're a mess, but in the end, we're never going to do this exactly, but we have them. They're equal to, plugging that in, the integral, I guess I changed from alpha to beta, this will also be beta. Right? Also be beta. Integral over beta, trace A D with the ordering minus sigma, beta star to the m minus beta to the n over n factorial m factorial. So you give me an operator A, I can derive what the coefficients are in the power series with that ordering. How do I do it? Well, I take the operator, I take its trace with this guy, and then I look at these moments of it. And that, in principle, are the Cn. Now, we're never going to actually do this, but we have them. Why? Why is this interesting? Well, voila! Now I have what is the A sigma representation of the operator. Well, by definition, it's take this guy in this operator ordering and evaluate it where I make the substitution. That's what I just erased. A dagger goes to alpha square, alpha star. A goes to alpha. So here it is. This is some number. B dagger plus sigma theta evaluated at A dagger goes to alpha. A dagger goes to alpha star. That was our definition. Right? And what is that? Well, so that's going to be, alpha star, the n, alpha, minus, which one was which? Which one had to the n?
Dagger?
The dagger. And of course, once it's unordered, that's that. That's our function. That's what we said before. Yeah.
So every possible ordering rule corresponds to a value of sigma?
Correct. So there are only three we ever care about. The others, in some sense, have no physicality. They have there's a math. I mean, it is analytic in sigma. In the same way I can do, I can define gamma functions beyond factorials, right? I can have some kind of analytic continuation kind of thing. But these are the three orderings that we care about. Symmetric, normal, and antinormal. But in principle, any one of them. Okay? So, finally, when I make that substitution, what do I got? My sigma ordered representation in phase space of the operator equals integral over beta, the trace of the operator with d minus sigma. And then once I put in that, it doesn't matter what order that's in, because once I make the substitution, everything commutes. And that's e to the alpha beta star minus beta star. And that's the key result, or a key result.
Isn't that alpha star beta second term?
Yeah. Okay. So, this tells me that to get this ordering of the observable written on phase space in this ordering, what I have to do is I look at its trace inner product with this guy, and then I Fourier transform it. This is the Fourier transform in 2D. Keep that in mind. 2D meaning x and p. So, in particular, if my operator were the density operator, so for the density operator, so we're looking at representations of the state. I'll write this rho sub sigma. I won't explicitly write out the alpha and alpha star anymore. It'll be clear. That's equal to the integral over beta, normalized by pi, chi minus sigma of beta e to the alpha beta star minus alpha star beta. Where chi is the expected value of the displacement operator for that ordering. That is equal to the trace of rho with the of that ordering beta, which is the characteristic function of the distribution. Yes, I don't know. You have a question?
So X and P are related, I mean, they are themselves conjugate variables and
I'm sorry, X and P are?
Conjugate variables in terms of Fourier transform, right?
Yes, indeed.
So here when you're doing the 2D Fourier transform.
Yeah, so this is different, it's true. It's a little bit confusing. Now I have a Fourier transform on phase space. So it's not that X is the in this case, it's not that P is true, it's a good point to emphasize. I'm not looking at P as the conjugate to X in Fourier space. I'm looking at, there is a phase space, there's a distribution on phase space, and now I'm looking at the Fourier transform of the whole phase space. So there's a conjugate to X and a conjugate to P. You have to open up your mind and allow that possibility. So I can just say, if you have, I have some function, forget you ever knew quantum mechanics, and you just said, here's some function, X and P. It's some distribution function on that. I can now Fourier transform that image, that function, and there's a Fourier conjugate. So this is my alpha, and now which is X plus IP, and now I have a beta, which is a Y plus I don't know, I don't want to, Q. Okay, forget about that. And this is, you know, the Fourier transform of that. Of course, it looks something like that. That's the Fourier transform. So alpha and beta are the conjugates. I'm taking the Fourier transform on phase space. That's what we're doing. Yes, Colson.
I assume that this generalizes in a very straightforward way if you have a polarization on a number, for example. So you have more than one A operator, as long as they commute.
Sure. So if I have multi-modes, indeed. I mean, then I just, each one, if they're all commuting modes, then there is a multi-mode quasi-probability distribution on the whatever the whole phase space is. We're going to talk about that soon. Okay, so I have my rho, and just as in the classical theory, we have the distribution function on the phase space and the characteristic function on the phase space. The characteristic function and the distribution function are conjugates, according to the Fourier transform. Now, in order for normalizations, we'll see by definition, we typically we define the distribution function W sub sigma as 1 over pi times this, which is then 1 over pi squared, the characteristic function e to the alpha beta star minus alpha star beta. That's just, we just define those. That's just how it's defined, just so that was, so the normalization is how we'd like it to be. And as I said many times now, and I'll just say again, W0 is defined as the Wigner function. W plus 1 is called P. P of alpha. And this is the Glauber Sudarshan. P representation. And W, I'm sorry, the minus 1, minus 1. W plus 1 is called Q, and that's the Husini representation. So these different representations of the state on phase space, which were historically defined completely independently for different reasons that we'll see in a moment, are actually all related to one another through these different operator orderings. And that was Cahill's thesis. Okay. All right. So now, another thing we introduced last lecture that I'll now return to is the Fourier transform of D. I mean, notice what's here. What's here is this is equal to the trace of A with an operator I'll call T minus sigma of alpha, where, I guess I should write another above. So, just looking at this, I see that this is equal to the trace of A with an operator we'll call T, where T is the Fourier transform of D. Right? So another way to look at these distribution functions is that instead of first projecting onto the plane wave and then taking the inverse Fourier transform, I can just directly project onto these guys if I know what they are. Right? Let me just check on one thing, because I can never remember how the factors of damn pi come in, and I would like to get that right, so I'll try. So this is equal to this. And as I said, if this is equal to, if this is like the quantum operator that's a plane wave, the Fourier transform of a plane wave is a delta function, right? So this is equal to a delta function that is localized where alpha is A and alpha dagger is a star ordered. And there's a factor of that. So that's another way of writing, and you'll see that, like if you look at Scully's book, he writes the Wigner function and so forth in terms of these guys. But of course, we will, in the same way you do all these different ordering, all these different approaches, there's many ways to skin the cat or the fish. All right. So that's interesting. In particular, the following. So we had this business, that the D's form an orthonormal operator set. And I could, by doing that trick, I could put the thing anywhere where I like. Put it here, put it like that, right? So we had that. And by doing the Fourier transform, this is also true about the T's. Put the plus here, I put the minus there. Plus here. Put the minus here. So with that, I can once again look at, say, the density operator written in this ket-like form, and what I see is that. It's the same thing we did before, but now with the T's rather than the D's. And in particular, what we see now is that the density operator is equal to an integral over the space. This is what we just said. This is the representation, this is what we just had over here, the representation of the operator with respect to that ordering. So, we have the following. My density matrix is equal to a weighting of the distribution function weighted by these operators. Now, the question is, did I get this backwards? I got this backwards somewhere. Sorry, let me just check on one thing because I've got one thing backwards. I don't quite see where it happened. no, it's good. Okay, sorry. Got myself confused, but now I see. You'll see why in a moment. Okay, so this is useful. This says that I can look at the density operator as a weighted sum of these P operators, weighted by the distribution function. In particular, what I see now is the following. This is where I started the lecture, but jumped the gun. Let's look at the expected value of A. Well, that's equal to the trace of A with the density operator. And what is that? Well, let's plug in this. That's equal to the integral over the phase space, the distribution function, the trace of A with T. And what is that? And that's where I got confused. This is a minus sigma, which it has to be. That's what I was just thinking. So this is a key result. Remember where we came from before we went down this rabbit hole of all these detailed math. What we were looking at was trying to get something that looked like the classical Liouville theory, where we had distributions on phase space, and we had observables that were functions of the canonical variables, and if we wanted to look at things like the expected value of observable, I would just take my observable and integrate it with the distribution function, and that gave me the expected value of angular momentum or energy or whatever. This is the quantum version of that. This says I can write the expected value of an observable by integrating that observable represented on phase space with a probability distribution, or quasi-probability distribution. The key here is the sigma and the minus sigma. So if I have the normally ordered representation of W, of the density operator, I have to have the anti-normally ordered representation of the operator. If I have the anti-normally ordered representation of the density matrix, I need to pair that with the normally ordered representation of the observable. If I have the symmetric order, then they're both the same. And that's going to be important in the physics of this. Okay, so, good. So now let's talk about the properties of these distribution functions and what they're useful for physically. Well, firstly, they're real. So if I look at the complex conjugate of these functions, well, that's equal to the according to this is equal to conjugate of the trace of rho with T sigma star. Right? By definition, And this is then equal to the trace of rho with T dagger of minus sigma. But T dagger is equal to T, the Hermitian, that was a delta function. So this is equal to, there's pi in there. The trace of rho, like that. So it's a real function, okay? All of these functions are real. The Wigner function, P function, the Q function, they're all real functions. Normalization. So the trace of rho, well, there's lots of ways to look at this. One, let's look at it in terms of the integral over the Wigner function is the trace of this. And that we never derived. That's a fun homework problem. That's equal to 1. So this, that's why the pi was put in there, so that my quasi-probability distribution has a simple normalization without the pi in them. Okay, so this is 1. Normalization. No matter what the sigma, no matter what, whether this is the P function, the Q function, or the W function, they're normalized. If I were to look at this in the terms of the characteristic function, this is equal to the characteristic function for minus sigma at the origin. Challenge for you. Okay. A little bit of Fourier analysis. All right. However, so this looks like a probability distribution on phase space, and it kind of quacks like a probability distribution on phase space, but it's not necessarily a probability distribution on phase space, because although it's real and normalized, it's not always positive. So though W for any sigma is real and normalized, it's not necessarily positive. If it were everywhere positive for all alpha, well, then it's a probability distribution, and I'll go home. Okay, now we come to the question of existence. I know this is a deep question, and it's kind of late to be getting metaphysical. But we want to know whether or not these functions actually, did those power series converge to something that was a function? How do we know? So to address this question, what we do is we think about Fourier analysis. So what we have is that the Wigner function, or not the Wigner function, but whatever quasi-probability we're looking at, it's the Fourier transform of quasi-probability distribution, the characteristic function. All right? So this exists if this Fourier transform exists, right? But what is the condition for this Fourier transform to exist? Well, we kind of know that from our from quantum theory and wave mechanics that if we have square normalizable functions, then we can go from one space to the other. So the condition for this is that this require the integral over all space of the quasi-probability distribution squared to be finite. The pi in there is finite, whatever the finite amount. So if the characteristic function is square normalizable, then the bigger function, or whatever function this is, exists. Of course, the same thing is true. This, by definition, this is also equal to this. Because of, you remember Parseval's theorem? For Fourier analysis, about the square of the Fourier transform average, integrated over, it doesn't matter which space is the time domain or the frequency domain. So this is what we require for this thing. So now let's look at them. Are these functions, does the function, do these quasi-probability distributions exist or not? All right, so consider the bigger function. Okay? Let's look at the trace of rho squared. So that's equal to the trace of rho with, I'll write the representation of rho with respect to the characteristic function. Okay, this was rho written in terms of the characteristic function. And that's equal to, this is one of this dagger. So this is then equal to this, which is just what we wanted. So the trace of rho squared is the integral of the square of the distribution of all space, right? What did I do? I brought this inside, and the trace of rho with that was chi star. That's what I did. So, this is the trace of, and is this finite? Yeah. If it's a physical state, this is less than or equal to 1. So, this is always a square normalizable function. The characteristic function of the bigger function is always square normalizable if I have a physical state. For symmetrical ordering, square normalizable. Okay. And so, what that means is that the Wigner function is always a well-behaved function. Very good boy. for physical state. Okay, that's nice. What about the other guys? Consider the receiving function. Q representation. Well, so what is the characteristic function we need? What we need is a character, this is, so remember Q is equal to W, it's the normally ordered representation, right? So that means that the characteristic function we need to look at is this one, which is equal to the trace of rho with d minus 1 of alpha, or beta, whatever, doesn't matter. It's a dummy. And that's equal to e to the minus alpha squared over 2 times the trace of rho with d beta, which is, sorry, beta. And that's equal to e to the minus beta squared over 2 times the guy for the symmetric. So, what we learned from this is that the characteristic function of the Q function is really, really well behaved. I mean, really, you're cutting off all those high frequency components with this Gaussian. And so if this certainly is a tempered function, and so the Q function always exists and is well behaved. However, let's consider the P function. Now we need to worry about this guy. That's its characteristic function. And that is equal to e to the plus beta squared over 2 times the symmetric guy. Now we're in trouble. Big trouble. Because this thing's blowing up. And unless this thing falls off at least as fast as e to the minus beta squared over 2, this thing will not be square normalized. So not in L2 on the real plane, or complex plane if you like, unless this guy falls off at least as fast as e to the minus beta squared. If it falls off that fast and this is a constant and then the P function is a delta function, then we're okay with that. It's like having a plane wave. So the P function mostly doesn't exist. Come back to what that means physically right now. Okay, so the Q function always exists, the W function always exists, but the P function doesn't. Let's talk about now some of the further properties of these guys and their use. Rossini. Q is equal to 1 over pi, the trace of rho, again, it's the normally ordered representation, which is equal to 1 over pi, the trace of rho with t minus 1. Now, here's something that will blow your mind. T minus 1 alpha, which is the Fourier transform of the, this is equal to the Fourier transform of the, with antinormal order. You know what this is? The projector onto a coherent state. Which is why you remember, and you brought up a good point after class, I said, you know, what the heck was going on? We had this fact that these projectors on the coherent states were a complete set, but they weren't orthogonal to one another, right? They were overcomplete. That's because what they're orthogonal to is their bizarro twin in the other symmetry. That's what they're orthogonal to. You have to go from anisymmetric order to symmetric order. Now that's a much uglier function, but we don't use that one. This one we use all the time, because look at this. What does this say? Let's plug that in. This is equal to that's the Rossini function. No one in their right mind would ever write down the Rossini function as some, you know, horrible projector on the inverse Fourier transform of the. No, the Rossini function is just the square of the amplitude in the coherent state. That's what, you know, if you were to say I have a wave function, if this is a pure state, let's say rho is a pure state, then this is equal to the square of the amplitude, and that, and there's a pi to make it normalized. That's the Rossini function. That's what Rossini wrote down because it's a natural thing to think about. If I have a state, I want to know what is its representation on phase space, I just look at its projection on a coherent state and square it. So to get the normally ordered representation, all you really have to do is project on a coherent state. If I look at, so A plus 1 of alpha is equal to that. Okay, so that's nice. What that says is that the Rossini function, well now it's clear why it always exists. It's just the square of that amplitude. That's a physical state that always exists. And moreover, it's always positive. The Q function, the Rossini representation, is always positive. So it looks like we can go home because I have a representation here of quantum mechanics on phase space in terms of an honest-to-God probability distribution. This thing is a normalizable, everywhere positive function. So I can just sample from the Q function with statistics, and I've done quantum mechanics.
The Rossini function itself is probability, right?
It's a real probability function. So why is this not the whole story? Why can't I just treat this, the world, then just sample, there's always a classical distribution of X and P. And here it is. And this, I could just flip coins, do Monte Carlo on my MacBook Pro, and I'm done. And simulate classical quantum mechanics with a classical probability distribution.
Is it because there's squeezed states?
No matter what. I mean, this is a positive distribution. I don't care if it's a Fox state. This is always positive.
Your observables don't always be
Exactly. You have to remember that we have this bizarro duality between the normal order and the anti-normal order. So while the Q function always exists, it is paired with an observable in anti-normal order. And we just said the anti-normal order stuff doesn't exist. So if I wanted to look at, for example, the expectation value of an observable using the Q function, I would integrate over phase space. I have my honest-to-God probability distribution, but I have this horrible A-1. The anti-normally ordered representation of the observable. And this don't exist usually. For the very reason that the P function doesn't exist. The anti-normally ordered representations blow up. This is not a real, this is something that would be multiple derivatives of a delta function. So there is no classical description, generally speaking, of the stuff. Even though Q is positive and everywhere exists, this thing is yicky. So the Q function, while it always exists, is rarely useful. It's used in terms of getting sort of, you want to sort of see what does something look like on phase space. You can just do this simply. But it's not useful for calculating anything. Because you can't calculate this. Okay, what about the P? Now let's go to the P function. The louder. Now rho is equal to right? No, minus. And we just said, oh, look, there is something very cool over here. Look what that is. Let's plug it in. This is what we started with before we did all this crazy math. If we wanted to think about representations on phase space, we thought about them as statistical mixtures of coherent states. That representation is the one that corresponds to the anti-normally ordered rho. Which usually doesn't exist. But if it does exist, then we have a classical description. It's what we call classical light back, in December, when P was positive and existed. And moreover, what we see here is that if I look at the expected value of rho, that's equal to the phase space average, not rho, observable A, which is the normally ordered representation of A, which always exists and is well behaved. And that's why we introduced the P function, because back in the day, when we were talking about photon counting, when me and my papa were sitting out there on the bench, you remember those old days, and we said if we wanted to calculate counting statistics, we need to look at normally ordered expectation values. In order to look at normally ordered expectation values, we have to pair that with the anti-normally ordered representation of the state. That's what we've learned now. And generally, that if the state is coming from something quantum mechanical, this is a bad function. It doesn't have a classical analogy. It's not a classical statistical problem. And so we'll look at, for example, what is the P function for a Fock state? It's not at all a well-behaved function. Couldn't interpret photon counting that way in terms of statistical mixture of coherent states. Okay, what about Mr. Professor Herr Dr. Wigner? So the P function is useful for making predictions, like photon countings and for thermal light. But it's not useful if we have something that's truly a quantum state. The Wigner function is the perfect harmony. It's the yin and the yang. It's the coffee and the cream. Because everything is symmetrically ordered, and thus everything exists. So if I look at for the Wigner function, the expectation value for the Wigner function, the expected value of the observable is equal to the integral over the Wigner function of the symmetric representation. And everything's well behaved now. And now we have a way of sort of looking at any time and saying whether or not there is a classical statistical prediction of what's going on by asking the question about whether or not it's always exists, is it not always positive? If it's negative, then there's not a classical statistical description of it. Right, so let's see. Where are we? Yeah. So other properties of the Wigner function. Now, Wigner's formula. When Wigner wrote down when he wrote down the Wigner function, he didn't do it in terms of all this fancy Cahill math. It was done in a different way. So let's look at for a pure state. The Wigner function that Wigner defined was this. Integral over a dummy variable. Displaced a challenge, as we will maybe have as an assignment, is to show that this is in fact the same thing that we had with the displacement operators and all the other jazz. So what this looks like is two wave functions, one displaced one a little bit to one direction, one to the other, and then you look at the interference between those two waves and you look at the Fourier transform of that. And that was the distribution on the phase space that Wigner first wrote down. This is the same thing as W of alpha of that state with a factor of 2 somewhere. Because alpha is x plus p over root 2, and you gotta normalize it the same way. Yeah?
This allows me to ask a question about before when you said that W is square integrable.
Yes.
So that's, I can see that W is absolutely integrable because that gives you the square of the wave function. And that's a probability assumption.
Right.
Here it looks like you're taking the fourth power of the wave function and saying that that's integrable. when you say that W is squared. So
Um,
what's going on?
yeah,
Why is it so automatic?
I agree that it's involving the fourth power. I think if the function itself is square integrable, then the square of it.
Not at all. Think about integrations around the origin where the function diverges a little bit. If you square it, it's even more divergent. You
True.
can throw it.
Yeah, that's true.
If the function is bounded, it follows immediately.
Yeah. So what is? Think about that a little bit. I mean, what is certainly true is that what I claim is that the trace of rho squared is equal to the integral of the square of the bigger function. That is what I claim. With some factors of pi that I may not got right. Now, if it's a pure state, then this is 1. Okay? So now the question is, how does this translate into, if I look at this guy and I square it, I've never done this, so, and then look at it, there's lots of Fourier transforms going on. And it must be the case that at the end of the day, this is actually equal to the square of the wave function, not the fourth power. It must come out that way. But I'll work that out. We'll look at it for next time. Okay, but there's a couple of other things I want to say, and keep you just a few minutes late, just so we can complete these few thoughts. And then next time we'll do a couple of examples. Okay. So how did Wigner come up with this function? Well, what Wigner was looking for was a function on phase space that satisfied the following important property: the property of marginals. What do I mean by that? Well, so I have the Wigner function is supposed to represent something like a joint probability of the two variables, x and p. We could talk about the marginals as the probability distribution of one variable averaging out all the rest. So what we seek is that if I look at the probability distribution of x, which is the integral over p of the joint distribution, that is supposed to be the square of the wave function. Or more generally, for a mixed state, this. And in addition, I'll make the script EP so that not to be confused with momentum. The probability distribution on momentum should be obtained as the marginal distribution of the joint distribution integrated over x. And this is supposed to be the square of the momentum space wave function. Or more generally, for any quadrature, it should be the case that if I look at the probability distribution of that quadrature, which is supposed to be the square of the representation with respect to that quadrature, that's given by the integral of the conjugate quadrature. And the only function that does that is the Wigner function. And that's how Wigner derived the Wigner function. He was looking for a function whose probability distributions on x and p are what we know from quantum mechanics. The square of the wave function is the probability distribution on x, and the probability distribution on p is the square of the momentum space wave function. And this is the only joint probability, quasi-probability distribution on x and p whose marginals satisfy that property. So what I want to show you is the icon for our website and what the heck that has to do with it. So let me just conclude with that.
Should I keep filming this?
What?
Should I keep filming this?
Are we out of juice?
No, I just wasn't sure if you wanted this icon on the.
Yeah.
Okay.
I mean, we could. There's no reason not to. I'm not going to show. I'm not going to show anything to in comparison. You never know. Yeah. Come on. Okay. Right. Okay, so what am I showing? This is the, our webpage. And this is taken from a paper stolen from a paper by Philippe Grandjean, where it is showing us the Wigner function for different quantum states. It's a function of two variables, so the surface is the Wigner function, is a function of x and p for different states. And what's being shown as the shadows are the marginals, okay? So if you ever wonder what you're looking at when you're looking at our webpage, that's what we're looking at. This is, guess what? Coherent state. This is a coherent state. It's localized at x and p, and it's got Gaussian wave functions as its marginals. As we know, a simple harmonic oscillator, the ground state, or a displaced ground state, is Gaussian in x and p, and this is the joint distribution. What's this? Squeeze state. Now notice, this is everywhere positive. That's interesting. We'll come to that in a moment. Maybe, a moment meaning next week. Where, although the squeeze state is non-classical from the point of view of the p function, it's classical with respect to the Wigner function. So there is a kind of classical, a totally classical picture in terms of parametric amplification that you're doing in your homework. That just is, I can just think about this as a classical distribution on phase space, and some of them get de-amplified and some of them get amplified. It's perfectly classical. It's just that those fluctuations really couldn't have ever been produced by a classical current. What is this? You have a guess?
Fox state.
That's a Fox state, right? I mean, it's a state which has a definite energy, which is like a, a circle on phase space. And notice that its marginals, these are the Hermite polynomials corresponding to n equals which? 1, because it's got one node, right? These are the squares of the Hermite polynomial times the Gaussian. But notice, it's negative. So this state is certainly not describable in terms of some classical statistics. You could think about it as the different points in phase space are kind of interfering with one another. And this state, which is the most interesting one, really, is what we call the Schrödinger cat state, where this is meant to represent two localized distributions that are well separated compared to their uncertainties, where if I'm over here in phase space, I'm alive, and if I'm here in phase space, I'm dead. And I'm in a superposition of those two, and what we see is that it's not just in the Wigner world a superposition of alive and dead, but all the quantum interference between alive and dead that happens between those. That state, again, if I looked at it, it's a superposition, as you notice here, in position. And that's like two slits, right? You present and you'll see in momentum space interference fringes, right? So that's what we're looking at when we look at the projections. So that's a lot of fun, isn't it? Yeah. All right. We will just do a little bit of I wish I'd finished this today, but it's just too much to do in one shot. We'll do a couple of examples on Tuesday. Thanks for sticking around. Have a good